In this video, we're going to formalize some ideas about congruency mod n. Now, you've seen how to work with congruency mod n in earlier courses, such as your discrete math course. And if you've had number theory, you would have seen it in number theory as well. But in order to work with congruency mod n and abstract algebra, we have to formalize exactly what we mean so that we can deal with proving theorems about it. And in this video, we're going to start that formalization process. The first thing is I actually want to make a formal definition. We are going to let n be a fixed, positive integer. And we are going to say that k is congruent to L modulo n if and only if n divides the difference k minus L. And I do want to point out that n divides the difference of k minus L means that we can find an integer q such that k minus L is equal to q times n. And we can go one step further. We can rewrite this equation. And when we rewrite this equation, we can say that k is congruent to L mod n if and only if we can find a q inside Z such that k is equal to q, and my handwriting has gotten weird there, is equal to qn plus L. Now it turns out that this particular relation on the set of integers happens to be an equivalence relation, and we need to prove that as a formal theorem. So, theorem. Congruency mod n is an equivalence relation on the set of integers. And I actually want to look at the proof of this. Now, an equivalence relation has three properties. An equivalence relation has to be reflexive, symmetric, and transitive. So to prove that congruency mod n is an equivalence relation, we have to prove each one of those things. So part one of my proof is I want to show congruency mod n is reflexive. In other words, what I need to do is I need to show that if k is any integer, then k is congruent to itself modulo n. Well, here's the proof of this little fact. We're going to make a note. K can always be written as 0 times n plus k. And using that definition, that says k is congruent to k modulo n. So the reflexive property is done. Part two of our proof is that we need to show that congruency modulo n is symmetric. And in order to do that, what we've got to do is we have to show that if k is congruent to L mod n, then L is congruent to k mod n. Now, in order to do this one, it's easier to use one of the alternate definitions of congruency mod n. And so I want to go back and I want to look at that just very briefly. I want to remember that k and L, k is congruent to L mod n if n divides k minus L. In other words, if k minus L is equal to some kind of integer multiple of n. And we're going to use that particular property in the proof of part two. Since k is congruent to L mod n, we know that there exists a q inside Z such that k minus L is equal to Q times N. But now I can multiply this particular equation by -1, and so we get -1 times K minus L is going to be minus Q times N, but -1 times K minus L is the same thing as L minus K is equal to Qn, is equal to Q minus Q times N. And when we look at this, that's enough to say that L is congruent to K mod N by the definition of congruency mod N. The final thing that we need to do is we need to show transitivity. So let's move to the next panel and say that part 3 of our proof is that we have to show that the congruency relation is transitive. And to do this, what we're going to do is we need to first of all think about what that means. Well, what this means is that we need to show the following is true. If, I'm going to call it I, if I is congruent to J mod N, and J is congruent to K mod N, then we need to be able to show that I is congruent to K mod N. Now I have to go back and I have to think about the different ways about showing congruency mod N. And again, what I want to do is I want to look at that division idea. In other words, if we step back, I want to look at this particular way of thinking about defining congruency mod N. In particular, two integers are congruent mod N if their difference can be divided by N. So let's step back through to where we're trying to do. And I'm going to actually rewrite each one of these things in terms of that. This statement here is the same as saying that I minus J is equal to Q1 times N for some Q1 inside the integers. And this particular fact is saying that J minus K is equal to Q2 times N for some Q2 inside Z. And what I'm now going to do is I'm going to look at I minus K. So let's look at this. I minus K is the same thing as I minus J plus J minus K, and I can certainly put parentheses here. And by using this fact up here, I can rewrite this particular equation, this particular I minus K number, as Q1 times N, and using this fact here for J minus K, I can say that this is plus Q2 times N. And now I'm going to factor. So it does turn out that N divides I minus K, and hence I is congruent to K mod N. And since we've shown all three parts, we can now say congruency mod N is an equivalence relation.